All right, over the last couple lectures, we went over applications of the momentum equation, and I want to just do a quick review of the setup, the approach that we should take when using the momentum conservation equation. And hopefully through the problem set and working example problems, you'll come to appreciate that it's really easy to make simple mistakes. And a big one is sign errors. It is very, very easy to make a sign error on inflows versus outflows, positive momentum versus negative momentum, action versus reaction forces. So it's really important to set up the problem very carefully. Now, the example that we did in class, I guess it was on Friday, was flow in a pipe that goes around a bend. And we're interested in understanding the forces that are acting on this bend. I'm not going to go through the whole example here in this. I just want to use it as a way to go over the approach that we want to take in setting up the momentum conservation equation. So first of all, define your coordinate system. And that sounds trivial, but it's important. And say, for example, in this problem, we might be solving in the xz plane. And we're defining x to be left to right, and z being vertical on the screen. Second is going to be to choose your control volume and control system. Now, in a control surface. Now, in lecture, we talked about some aspects that you want to look for in choosing that control volume, like defining the faces to be at locations where you know something about the flow. So maybe you know the pressure or the velocity at these two faces. You also want to make sure that the control volume encompasses the interactions that define the forces. And so in this case, we want to know the force that's acting on the fluid in the bend. So we define our control volume to be this entire reach going around the bend from surface 1 to surface 2. Okay, third step is to sketch the forces and the velocities. And here you're choosing signs for these or specifying what you know or don't know about them. So, for example, we know that flow is going from left to right across face 1. We know that flow is going from left to right across face 2. So this is our v1 vector, and this is our v2 vector. Now, those vectors have x and z components, but that comes later in the solution. We also want to specify the forces acting on the faces of the control volume, or acting on the control surfaces. So here we have P1, A1 acting from left to right. Here we have P2, A2 acting against the control surface. So in this case, it's going up and to the left. We also have the force that the bend is applying to the fluid, and I'll call this F sub B Z component, F sub B X component. Make these capital B's, and that's a Z. Okay. So we have the Z and the X components of the force that we're looking for. And then finally, we have the weight of the fluid acting vertically downwards. Now, the momentum equation, remember, that's another thing I want to emphasize here, is to remember that the momentum equation is describing the forces on the fluid. So it's the weight of the fluid here. It's the force that the bend exerts on the fluid. It's the pressure forces acting on the fluid. And of course, the fluxes of momentum are in the fluid as well. All right, step 4, define the unknowns and solve. Now, in defining the unknowns, frequently, we're going to find ourselves wanting to use other equations, mass conservation. And as we'll see in the next lecture, energy conservation. Those are additional pieces of information that can be used to define the unknowns and then solve the equation for whatever you might be looking for, whether it's a force or a velocity.